Okay, we're going to start chapter 3 and then section 3.1, tangents and the derivative at the point. Up to now we've been discussing limits, and the discussion of limits was really to get us to this thing that we're going to call the derivative. Now, for those of you that have had calculus before, you're going to know that there are a whole lot of shortcut ways to find derivatives, and we will get to those shortcuts or those basic rules. We will get there, but until we get there, you can't use them. So on a test or quiz, before we get to those basic rules, we expect you to do it this long way with the limit, or what we're going to call the definition of the derivative. So even though you may already know how to do some of the shortcuts, you're still going to need to know this definition of the derivative, because I am going to ask about it every now and then. Okay, so we're going to start with the motivating question of what caused mathematicians to come up with this thing called the derivative. So down here we've got a function. Shown below is a function y equal f of x, that's the curve, with a secant line passing through the points x naught, f of x naught, and q, which is x naught plus h, f of x naught plus h. So the curve is my function f of x, and by what we mean by secant line is just a line that goes through a curve in 2 points. So this first point here has an x-coordinate that we happen to call x sub naught or x sub 0. And then remember, y-coordinates are always found by plugging into the function. So if my x-coordinate is x naught, my y-coordinate is going to be f of x naught. Then I just move over some positive distance. I'm going to call that positive distance h, come up with a new x-coordinate, x naught plus h, which then there's my x-coordinate, x naught plus h, and my y-coordinate is going to be f of x naught plus h. That I always find y-coordinates by just plugging the x-coordinate into the function. And so then the question I have off to the side is, what is the slope of the secant line PQ? Well, that's easy. That's just algebra. We could just use the formula for slope. And so the formula for slope is y2 minus y1 over x2 minus x1. So in this case, f of x naught plus h minus f of x naught all over h. So there's the slope of the secant line. Nothing special there, no calculus necessary. That is just algebra. So that's pretty boring. So the next question we're going to get here is same curve, but now I've drawn a tangent line at P. So instead of the secant line going through 2 points, this time I've drawn a tangent line. And by a tangent line, we mean that the line intersects the curve in just 1 point. At least 1 point in this vicinity. You know, I have no idea what the curve and the line might be doing in the third quadrant over here. I have no idea what it might be doing clear up here. But in this vicinity, in this neighborhood, that line intersects the curve just at 1 point, at the point P. And so the question here is, what is the slope of that tangent line? Well, we can't use the formula for slope. The formula for slope needs 2 points. I don't have 2 points, so I only have 1. So what we're going to do to investigate this is, as it says here, to investigate this, we'll move the point Q toward P and draw a series of secant lines. Now this is going to look kind of messy, but we'll deal with it. So the first secant line, and I have my pink pen in my hand, so there would be the first secant line. And then that distance is h. So then I'm going to move Q again, move it down there. And so I'll drop a vertical line there. So my distance h is right here this time. And my secant line is right there. And then I'll do it again. There's my next position of Q. And so h is right there. My secant line, right about like that. And let's do it one more time, right there. So h this time is right there. And my secant line, we'll just get it right in there, is right about there. I'm going to draw it both ways. Okay, so I have my point Q that I just keep moving down, and I see what the secant line's doing, and I see what that distance h is doing. So to investigate this, move the point Q toward P and draw a series of secant lines. And then the question I'd ask the class, but the classroom's empty, so I'll ask and answer it myself. What happens to the distance h as Q moves towards P? Well, if I look at h, starts here, 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 here. It's getting smaller. And it's getting smaller and smaller and smaller, but it's not getting smaller and smaller and smaller forever. H is getting close to zero. It's not going to get smaller and smaller forever. Eventually, Q is going to be right on top of H, or Q is going to be right on top of P, and so that distance that is the distance between the x coordinates, that distance is eventually going to get zero, or going to go to zero. We're putting a little mathematical notation in there. H is going to approach zero. Then what do the secant lines approach as Q moves? So now I'm looking at these pink lines, and what are the pink lines getting closer and closer to? Well, as I look at those pink lines, and if I was a real tech wizard, I have a little animation here, but I'm not a tech wizard. What I see in those pink lines is they keep getting closer and closer and closer to the tangent lines. That the secant lines approach the tangent line. Well, if that is true, we can then say what we've got at the top of the next page. So as Q moves, H approaches zero. We already saw that. And the secant lines approach the tangent line. We can see that. This would mean that the slope of the secant line approaches the slope of the tangent line. If the secant line is essentially becoming the tangent line, and that's what we can see, that pink line eventually kind of ends up right on top of the black tangent line, that means their slopes are going to have to be the same. This would mean that the slope of the secant line approaches the slope of the tangent line. Recall the slope of the secant line is given by, and we have it up there. I introduce a slightly new notation here, m sub sec, right there. M sub sec is f of x naught h minus f of x naught all over h. So we get to come up with this definition. The slope of the curve at y equal f of x at the point P, which is x naught f of x naught, is the number m sub sec, which is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. That what my little pink lines are showing me is that as h gets closer and closer to 0, as the limit approaches 0, as that limit approaches 0, the secant line lies on top of the tangent line, and we knew that the slope of the secant line is that. And notation-wise, this is wrong here. We got a typo. This should say at this point m sub tangent. It's the tangent line, not m sub secant. It's the tangent line once I put that limit on there. Without the limit, it's the secant line. With the limit, it's the slope of the tangent line. So we got a little bit of a typo there. Let's say m sub tangent. Now that particular limit there is so important in calculus that we give it a name. Definition: the derivative of the function f at the point x naught denoted by f prime of x naught. This is red. F prime of x naught is given by f prime of x naught equals the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h, provided the limit exists. There is the definition of the derivative at a point. You do not need to memorize this definition. I will have you memorize the definition of the derivative, but I'm going to have you memorize the definition of the derivative as a function. This is the derivative at a point. And we will stop this video here, and then on the next video, we'll talk about how to use this limit.